Hello, my name is Emerick. I'm from Shippensburg University, and my REU is sponsored by the NSF. My topic is shared shortest paths and graphs. I'll start off with some terminology. A graph is just a set of vertices and edges. Vertices are connected by the edges. This is a weighted graph. The weight could be anything from cost to travel on that edge or just the distance on that edge. A journey is any designated starting and ending point. So for example, here we have a weighted graph and the journey is from 0 to 8. The shortest path would be, given any path from 0 to 8, what is the shortest way to get there? So in this example, it would be this blue line here, with the cost being 12. So our problem was to find an algorithm to make the shared shortest path. What I mean by shared is that, for example, down here, if two journeys are sharing one edge, then the cost of that edge is divided by how many journeys are sharing it. So, for example, yellow and blue are sharing this edge, so this cost would be divided by 2, and so this total cost would be 2. So in my research, we were trying to find an algorithm to find this, but they also had to have no incentive to change. So basically, the journeys had to be locked into place. We call this equilibrium. In this graph here, for example, there is no equilibrium, and I'll explain why. So these two journeys are sharing, and the red one is not. However, the red is going to convince the yellow journey to share this middle edge, because if it does, this cost will be divided by 2, and the yellow will have a cost of 3, which is better than its previous cost of 4. And the red will have a cost of 4, which is better than its previous cost of 5. So now red and yellow will share this path, and blue will be by itself. And now that blue is by itself, it's going to want to share with red, and so this whole situation will keep bouncing back and forth. This makes finding an algorithm for the shared shortest path NP complete. This means that it cannot be done, the process cannot be finished in polynomial time, which means we basically don't want to wait for it to get done. It'll take too long. So what we had to do was create a heuristic to approximate this solution, or the shared shortest path. And I'll describe the heuristic that we made. First step is to use Dijkstra's method, which is just a algorithm to find the shortest path, the unshared shortest path. And so say we have 4 journeys, one from 4 to 11, 0 to 7, 2 to 12, and 8 to 16. We find the unshared shortest path for each one, yellow, blue, and if 2 of them are already overlapping, then they will automatically share this edge. And so we'll compute the cost accordingly and save this graph. The next step is to delete the edge that was being shared on. And then after that, we use Dijkstra's again to find the new unshared shortest path of every journey. And if one of these edges, if one of these journeys, the yellow or blue, got shorter, and then we save this graph as well. And so now we have 2 updated graphs. And we keep doing this process, we keep deleting edges and finding the new unshared shortest path. And now we have an ending result, which is sometimes the best result, but sometimes one of these updated graphs are better. And so we came up with some different variations of this heuristic to maybe make the ending result a little better. For example, one of them was to just check every edge to delete every edge instead of the shared edge. And so that gave us the best results. We also analyzed each updated graph. And so to do that, we used the minimum sum of all the costs, and that would usually be the best one. Or we used ratios like cost lost to cost saved and stuff like that. Some of the results that we came up with were, in 90% of all the graphs tested, if a journey saved, then it saved at least 8% of the cost that it started with, which was just Dijkstra's method. And in 75% of the graphs, they saved at least 15%. So those are pretty good results. Some other results that we found that kind of seemed to be true. If a group of journeys are sharing and they split at any vertex, then the 2 groups will never meet back up at another vertex. So here's an attempt at a proof. I guess that's about it. Some conclusions are that this heuristic runs in polynomial time, depending on the vertices, the edges, and the journeys. Some future work is to try to avoid this non-equilibrium position, to create better heuristics or different variations of this heuristic, and just to get a better approximation.